Hello everyone, today we are going to talk about the security of macOS and iOS kernel drivers. And the title of our talk is It's the core of an Apple, how we analyze and find bugs in macOS and iOS kernel drivers. I'm Xiaolong Bai from Alibaba Security, and before joining Alibaba, I received my PhD degree from Tsinghua University. And I have published papers on the top 4 security conferences, including SNP using security, CCS, and ADSS. And my Twitter and Twitter, Weibo, and GitHub are both all BXL 1989. You can connect to me in these ways. And this is Spark.
Hello, everyone. My name is Zheng. You can call me Spark. I'm a security expert at Alibaba. I got my PhD degree in the CUHK, Chinese University of Hong Kong. My Twitter is Spark Zheng, and the Weibo is Zheng Spark. You can follow me on that and ask me questions. So today, we will introduce how to find bugs in the drivers. So here is the agenda. First, I will give an overview about drivers in kernel and user space perspective. Then I will talk new vulnerabilities on macOS, about 2 new vulnerability and exploit strategies, and how to do privilege escalation on the latest macOS. Then Xiaolong will talk about obstacles when analyzing Apple drivers, and we will introduce a new tool called Reek to do the analyze. So every driver is a kernel extension which shares the same space with the kernel. We know this is not a good design because if you control the driver, which means you control the kernel. We know that drivers always have more bugs than the kernel. A system daemon called kernel extension D is responsible for loading and unloading drivers. You can find the driver binaries on macOS in this path, system library / extensions. For iOS, the driver binaries are integrated with kernel in the kernel cache. You can download the kernel cache from from Apple's official website and analyze the kernel cache in Ada or JTool. For the drivers are programmed in C or C++. You can get the configuration file. The configuration file is the info list, info.p list. You can get the name of the driver from IO class and the user client name from IO user client class. And also you can get the libraries which are used in the driver. For example, KPI allocate and KPI lubricant. For drivers to communicate with kernel, they can use kernel APIs as known as KPI. For the KPI list, you can find the KPI list on macOS in this path. And for some basic, also KPI provides some basic models. For example, KPI allocate. It provides an open source framework called iOKit, which includes some basic driver classes. And for KPI lubricant, it is a restricted C++ runtime lib in the kernel. It does not include exceptions, multiply inheritance, and templates, but it is an enhanced runtime typing system because every class has an OS meta class object which describes the class name, size, parent class, etc. So here is an example of a simple driver. And this is the head file and the code file. You can get the name of the class in here. And all the drivers, All the drivers have the same parents called IO service, and you can use a micro definition to declare the constructor and destructors of the driver, because they have a parent called IO service, so you need to implement the virtual method of IO service. For example, the init, free, start, stop. In order to communicate with user space for the kernel driver, you need to implement the user clients. The user clients is actually a kernel objects which provide service to programs in the user space. You can create them in two ways. One is info.plist file. You can add IO service client class to claim a new user client, or you can implement a callback method of driver in the new user client method. So here is an example of a simple user client. But I recommend you to download some open source user client and drivers from Apple's official website. You can learn a lot from them. In order to implement a user client, you need to implement some callback methods. The most important one is the external method, which provides the methods that can be called in the user space. And also you can use client memory for type to share memory with programs in user space. And you can use register notification pod to register a notification pod for the user space program. And when user space program closed or died, it will call client close and client died callbacks. Also, there are some seldom used method. For example, get target and method for index. They are similar to external method, but it's in old fashion. So let's talk about the most important one, external method. This method has 5 parameters. The first one is called the selector. It is used to select method in the user client. It starts from 0. And for arguments, this parameter will pass the parameters from user space to the driver. And the dispatch is a struct representing the method to be called. And the target shows the user client for the method to be called on. And the reference will send the result back to the user space program. For the user line perspective, Apple provides IO-Kit framework for programming in user space to interact with kernel. But if you use some public explicit invocation in the iOS app, it will be rejected by Apple Store. There are some important APIs in IO framework. For example, if you want to interact with a driver, you first need to use IO service get matching service to get the service of the target driver. Then you can use IO registry entry create or set CF properties to get the driver's property or set the driver's property. Then you can use IO service open to connect to the target driver. Then you can call IO connect call methods to interact with the driver and call the driver's methods. Last but not least, you can use IO service close to close the connection of the driver. So here is an example of how to communicate with an IO-Kit driver. First, you use IO service get matching service to communicate to get the service of a IO-Kit driver called IO fireware local node. It will connect to the driver called IO fireware family. And then you can use IO register entry set CF property to set the property of this driver. Then you can use IO service open to open this service and get a IO fireware user client. After you get the user client, you can communicate with it, and you can use IO connect call method to call the driver's method through the connection. After that, you can use IO service close to close the connection with the target driver. Actually, APIs in IOKit framework are wrappers of mark trap, which are generated by MIG and eventually call into callback methods implemented by user clients. For example, if you use a userland API called IO connect call method, it is actually a mark trap in the kernel, and it will call the code which are generated by MIG and eventually call IO user client external method, which is the callback method implemented by the user client. Despite of strict sandbox restriction, some user clients in IOKit driver can still be accessed by sandboxed apps on iOS. For example, we through experiments, when confirm these available user clients and their corresponding IOKit device driver names on iOS 11. For example, the most important, the most famous one is IO service root. You can use IO service root user client to communicate with this driver on iOS inside the sandbox. Compared with kernel, drivers are always blamed for poor quality, so which makes them frequently to be used to exploit the kernel. A lot of bugs are used in real-world jailbreak. For example, for iOS 11, Electro jailbreak used the IO service root, which are found by RMBear. And for iOS 9, Pangu team used the IO mobile frame buffer vulnerability, which is a heap overflow in the kernel driver. And HITB used the IO HITB family vulnerability to do jailbreak on iOS 8. So we can still find a lot of bugs in the on iOS and macOS, and now I will show two vulnerabilities. The first one is information link vulnerability on the fireware family driver. As you can see, this is a function, and first, the out channel handler is a variable on the kernel stack, and it is initialized, and it will pass into the ISO channel create function. At last, it will be a result and send back to the user space. Inside the method, we can find that this variable will be passed into the add object method. In this method, we can see if we call this method too many times, the kernel will return an error. The driver will return an error that we don't have memory. Kernel key IO return no memory means we don't have any memory to allocate, and then it will do nothing for the out handle and just return it. So as we mentioned before, out handle is a variable on the kernel stack without any initialize. So after debugging, we found it will link 4 bytes information, which is an address on the in the kernel. So compared with kernel cache, we downloaded from Apple's website. We can get the kernel slide in the lower 32 bytes. After that, we can calculate and break kernel slide. Though we can only get the lower 32 bytes, but it's enough because the higher 32 bytes is always 0xFFFF80. So now we break kernel slide, KASLR. The next bug is in firewall family 2. This bug is a risk condition problem. It has a risk condition problem and can help us to control the PC register. In this function, we can see F memory, FMEM. So this is a member of class of IO firewall user read commander class, and all the user clients can read this F memory, and because we can control the parameters in the user space, so we can control the free of F memory. For one thread, this method has no problem because it will check the F memory before use it. But for multiple threads, it will have a risk condition problem. Because for one thread, we can free the F memory because we can control the parameters, so we can free the F memory. Then for another thread, we can use F memory to call create read command. In this method, it will use F memory to call something. But if we free this F memory in the first thread and then call it in the create read command, it will cause a use after free problem. So if we can allocate a same buffer with the same size as F memory, we can control the PC register. So after control the PC register, we can do rope. If we want to do rope, we need to send the rope chain into the kernel. A good candidate for the heap spray is IO registry entry set properties, because this method will call OS unserialized XML function. This function is a good candidate because a lot of drivers can be accessed and can be set. A lot of drivers property can be set from the user space. For example, IO HID event service, and the spread data can be read. You can use IO register entry create properties to read the spread data back to user space, and the head of the spread data is controllable. If you use Mac message, you can't control the head of the spread data. Here is a classic rope chain to get the root privilege. First, you need to do a stack pivot to control the stack of the stack, and then you use current process to get the pointer of the structure pointer of current process. Then you use proc ucredit to get the identity of the structure process. After that, you can use B0 to set CRUID, CRUID, and CRSVUID, SVUID to 0. It will set the process to root, and then you use thread exception return to exist kernel and return to user space. Then you can use setUID to get the root privilege. But for the latest macOS, some classic stack pivot gadgets are missing. So you need to find new gadgets to do that. Luckily, we find 2 gadgets which can do the stack pivot. For the first gadget, you can use IX to control RCX and then call IX. For the second gadget, you can control ISP through RCX and then jump to RCX plus 3.8. So here is the whole exploit process. First, you do a heap spray to spray the rope chain into the kernel. After that, you use our first you need to use the info link vulnerability to break the kernel slide, and then you can build your rope chain. After that, you spray the rope chain into the kernel. Then you use the risk condition bugs to control the PC register. After that, you use the PC register to jump to gadget 1 that you can control the stack. After control the stack, you can run the rope chain and get the root privilege and finish the privilege escalation. So here is a screenshots after a successful privilege escalation. Before our talk, we sent the vulnerabilities to Apple, and they gave us 2 CVEs about the information leak and the risk condition bugs, and fixed on the latest macOS 10.13.4. So that's my part. And then Xiaolong will talk more about our tool, Reek. Okay, welcome to Xiao.
Thanks, Mark. It's okay. Compared to these vulnerabilities, the way in which we find them is much more valuable. Actually, analyzing Apple drivers is not an easy task. Mainly because it reflects that these drivers are most closed-sourced and programmed in C++, and even for iOS drivers, there are lack of symbols. There are no symbols. So let's first look at how a driver binary looks like in Ada Pro. So let's first look at macOS drivers. From these 2 pictures, we can see that macOS kernel drivers have some symbols, including symbols for global variables on the left hand and for functions on the right hand. And also, we can find symbols for vtables in macOS kernel drivers like this. Even better, we can find the symbols for the methods that the drivers are going to provide to user space programs. Better, we can find that macOS drivers have function names. Their function names are kept and meaningful, and these function names can be demongled to get the argument types. So with these benefits, it seems that functions in macOS drivers, the compiled code can be partially human readable. It seems that we can understand this code. But actually, you can see that there are many function pointers. These function pointers are all virtual function calls. We don't know the real target, the real function that are called in with these function pointers. We don't know what functions are called here. So inter-procedure analysis can now be performed with this code, not only for manual review, but also for statistical analysis. And also, without knowing the structures of the classes, we don't understand this code. we don't know what member variables are set and what member variables are read. So we cannot fully understand macOS drivers. So how about iOS kernel drivers? Actually, their situation are even worse. You can see that this is a code of this is function names in iOS kernel drivers. You can see that these function names are meaningless. IDE Pro names these functions with just strings prefixed by sub. And also, there is no symbols for vtables. We cannot find where vtables are. And look at this piece of code. This should be a vtable. This should be a vtable, but we cannot find any clue about this vtable. What's worse, IDE Pro cannot recognize functions in iOS kernel drivers for most of the time. So let's look at the compiled code of iOS kernel drivers. We can see that the code is cannot be understood at all. Here you can see that the function names are meaningless, and the real targets of function pointers are unknown, and the variables have no type information. And also, like macOS kernel drivers, without knowing the classes structures, the reads and writes on class member variables cannot be recognized. So, in order to overcome these obstacles, we design and implement a new tool. This tool is called Ryuk. You may be wondering why we call this tool Ryuk. Because Ryuk is a famous character in the comic series Death Note. He is fond of eating apples, just like us. So we hope that Ryuk can eat all the code of the Apple drivers and tell us what bugs they have. So for now, Reek tries to recover symbols and solve our object-oriented features in macOS and iOS kernel drivers. So let's talk about the features of Ryuk. We design and implement Ryuk with below features. These features are mainly for solving the lost symbols and the object-oriented programming issues in binary code. The first feature is called class recognition and construction. In this feature, we identify classes' basic information, including names and sizes, and then construct classes structures in IDE Pro to represent these classes. And the second is vtable recognition and construction. This feature recognizes vtables and construct structures in represent these vtables. And the third one is recovering. Recovering function names. This is mostly done in iOS kernel drivers. And the fourth one is resolving variable and argument types. And the last one, but not the least one, is the US port. Let's briefly see what effects with these features. The first one, class recognition and construction. With this feature, we can create structures in IDE Pro to represent all the classes created in the kernel drivers. And with the second feature, vtable recognition and construction, we can see that in the previous picture, we know that iOS vtables cannot be recognized and figured and found. We don't know where the vtables are. But with Reek, we now can see clearly that this is a vtable for a class, and we can see that the entries in this vtable, what functions are in this vtable. And further, with this vtable recognition and construction feature, we create structures representing these vtables, and we can see that there are a lot of functions, virtual functions in these vtable structures. These member variables are all function pointers. So further, with the feature of recurring function names, we have seen that iOS kernel drivers don't have any symbols for their function. So, but with Ryuk, we now have symbols for the functions. We have names for these functions, and we know what they mean right now. And further, with the feature of recovering function names and resolving variables types, we can know. Maybe you can see clearly. We can know what classes are these variables, local variables, and we can know what functions, what virtual functions are called here. And a new advanced feature in Ryuk is called US support. This feature supports your action in Adapro for a better experience when analyzing Apple kernel drivers. You see that there is a virtual function call in this place in the compiled code, and you just want to see what's the implementation of this virtual function. So with Ryuk, you can just with a double click on the function pointer, and then you can directly jump to the implementation of this this virtual function. And here is a small demo of this function. You can see. Wait a second. You can see with a double click, you just go to the implementation. And also, you can choose the implementation of the child classes and go to the child classes implementation. This is a new feature. Oh, sorry. So you must be wondering how we implement these features and functionalities. For example, for the first one, class recognition and construction. In iOS, in macOS and iOS, there is a section called mode init func. This section lists a few initialization functions that are executed at the start of kernel drivers. We use these functions to implement our class recognition and construction feature. So we analyze these initialization functions. We can find that these functions call some registration function, registration function at the red line. And when calling these functions, we pass the drivers passing some basic information of the classes, including the class names, class size, and their parent class information. So we perform some backward slicing static analysis techniques on these classes to identify these arguments passed to the registration functions. And then you can see that we can get the class name and the class size and the parent class information from this code. Then we can create the structures representing these classes in Adapro. You can see, you can see that these structures represent the sets and their names. And for the second feature, VTable recognition and construction, we think that it is quite easy to implement on macOS because we have already shown that on macOS drivers, VTables have symbols and we know their addresses, so we don't need to find them. We just go to the name window and find the VTable symbols. So this is easy. But on iOS, it's quite complicated because I have already told you that there is no code feature or any symbol about the VTables on iOS kernel drivers. So there are many steps in order to implement this feature. The first one, we need to adjust the const section. This section contains all the VTables. So we must first know we must first adjust this const section to make it a little bit like VTable. Then we can do further analysis. And in this step, we mainly mark the data in this const section as addresses. For example, we make the left picture look like on the right side. And then in the second step, we utilized formation the previous initialization function again to locate the address of the class's meta class object. This meta class object is a hint for the address of the VTables, which will be used in the next step. So in the next step, we can get a cross-reference of this meta class object and find a cross-reference in the const section. And go to this cross-reference in the const section. We can find that this cross-reference is quite near it's quite near the real VTable. We can see that the cross-reference is 32 bytes ahead of the start of the VTable. So now we find the VTables on iOS. Then we can create structures in Adapro to represent these VTables. And I already said that these members in these structures are all function pointers. They are function pointers representing the virtual functions. So for the third feature, recovering function names, we mainly do it on iOS. Since I have already said that macOS kernel drivers have function names and have meaningful function names. So this feature is mainly done on iOS. And we only perform this analysis for virtual functions on iOS because we know that most classes in iOS kernel drivers inherit from basic classes in IOKit framework, and the basic classes are already IO service, OS object, IO the client class, exactly. But we know that the virtual functions in these basic classes have meaningful names. So we utilize the inheritance hierarchy to recover the unknown function names. For example, on the right side, we know that on the left side, we know that this IO surface root class is inherited from IO surface class, IO service class, and we know that it overrides a virtual function called IO service get meta class, this virtual function. So we know that this unnamed function on the left hand should be IO surface root get meta class. In this way, we recover many names for the function. So come to the fourth feature, recovering variable types. This feature is quite useful for analyzing in the compiled code. When we need to implement this feature, we first figure out the creation of variables. We mainly identify four kind of functions that are used to create and initialize variables. The first and the second are allocation functions, and the third is constructors, and the fourth is cast functions. From these functions, we can know that we can know a lot of information a lot of type information about the affected variables. For example, in the first function, estimate class allow class with name. We can know the result. The result of this function should be object of iOS class. So we can give a type of that variable iOS. And then we can perform type propagation on these affected variables and solve the types and further solve the types of all affected variables, including the local variables and the member variables of classes. So now you can see that this code is much more understandable. For the final feature, which is called UI support, the purpose of this feature is mainly for analyzers to have a better experience on analyzing macOS and iOS kernel drivers. For example, if as I have demonstrated, if you want to jump to the virtual functions implementation, you can just double click on the function pointers. So how we implement them? We register actions to many UI events. For example, the double click events, key events, key down events, name changing events, type changing events. We register actions to all these events in HITB Pro, and to check what is going on here. And if you are, for example, if you are doing a double click event, if you are doing the double click on a function pointer, we know that which function you are doing double click on, and we can just open a new window to show you the code of the virtual function implementation. So with all these features, Reek can assist both manual review process and static analysis. For example, for manual review, the code now is much more human readable and understandable. And you can also interact with the HITB Pro in a more convenient way. And for static analysis, we know that variable types and the targets of virtual function calls are determined right now. So we can further build a call graph and a control flow graph on these variables, on these functions, and further static analysis can be easily done. So this is all about Ryuk. So in our talk, we have explained and illustrated 2 new CVEs in Apple drivers, and also present how we exploit them for privilege escalation on macOS. And finally, we have shown a new tool for assisting the analysis of macOS and iOS drivers. And most importantly, please fork and start Ryuk on GitHub. This is the address of our Ryuk, and it's open source now. Please follow. And that's all. Thank you. Any questions?
Are there any questions? None? Then I'd like to thank Xiaoling Bei and Min Zheng very much for your talk. Thank you.
Okay, thank you.
Big round of applause.